we talked about the work being done by gravity and the work being done by you in lifting the box. Does that sound like what we did? All right, so let's begin there with the idea that we lifted this 15 kilogram box up into the air, and the box is now in the air above the ground. And I think we lifted it 5 meters, and we said that the box was 15 kilograms, right? 2 meters, all right, 2 meters. And the box was 15 kilograms? So we said the work done by you was 300 joules, and then the work done by gravity was negative 300 joules. Do you remember all of that? Okay, good. I want to show you something, and then I want to come back to this. So what I want to show you, back in this problem, we would say that the net work is equal to 0, right? If I add all of these up. So the word net here means to sum. So when I use that word, this problem, the net force was 0. We were lifting the box at constant velocity. So since we knew the net force was 0, we knew at the end that the total work done was going to be 0. I want to come back to this for a minute. Did I go too fast? Or you try to write me then? If we drop the box, right, it's going to fall to the ground, correct? How much work will be done by gravity? I'm not asking a hard question. If we drop the box, it's going to fall how far? 2 meters. And what will be the size force acting on the box? 150 newtons. So if the box falls to the ground, it will be moving, right? How much work will have been done on it? 300 joules. These aren't hard questions. There's only one force acting on it now. So the work done by gravity this time will be 300 joules. Is this work done by an unbalanced force? That has to equal the change in kinetic energy. That's exactly what this means. The work was done by an unbalanced force. So the box now has 300 joules of kinetic energy just before it reaches the ground. If it was dropped, the initial kinetic energy was 0. So the final kinetic energy will be whatever the box has just before it reaches the ground. If I want to know how fast it's going when it reaches the ground, I can just set this equal to 1/2 mv squared and figure out how fast it's going. Please do so. This should be super fast. Use your calculators and all your fancy spiffy stuff. David, how fast was it going? I think it's the square root of 40, right?
Yeah, it's 6.3.
If you know how much work has been done, you should be able to use it to figure out how fast something's going. Let's practice this one. I want to go back to this problem for just a minute because there's something important here, and I kind of need to emphasize it. I have 8 minutes. I want to get rid of all of this for just a minute and just think about the box. I lift the box in the air. Perhaps perch it on the end of like a shelf or a bookcase or something. So I lifted the box up and placed it there. Nothing has really changed about the box. It's just higher up than it was before. Would you guys agree? But at any moment, it could fall off the bookshelf. And we know, based on how high it is, how much work had to be done to get the box up there. Now, we can recognize that if I lift the box higher and put it on a higher shelf, that when it falls, it will be going faster. That makes sense? More work was done on the box, therefore when gravity brings it back down, it will convert more of that energy to kinetic energy. People understood this idea, and although there's nothing really different about the box, there does seem to be something about having the box up on a shelf that means it could fall to the ground and do something. Now, the box doesn't really matter in this case, but if anybody's ever swung a hammer before, you understand that if you lift a hammer up and you bring it down, you let gravity help you bring it down. That's how a sledgehammer works. Sledgehammer's whole premise is that it's really hard to get up into the air, but then once there, gravity can do all the work bringing it back down. Does that make sense? This is also why you build castles on the top of hills. You don't build them in the middle of the valley. You lug all the rocks up there, build your huge castle, and you make it defensible because you can store stuff in there that you can drop on opponents who are trying to raid the castle. So you never built the castle in the valley. That's dumb. They can rain stuff down on top of the castle. You put the castle up high. That way, when the Mongol hordes come, you ring the bell and all of your people, your serfs, come into the castle, and the lord of the castle is there to defend all the people that are supposed to be serving that lord. And they do so, of course, by having stored all sorts of stuff in the castle they can drop on their enemies. This concept of being able to have this stored material isn't just a concept. We call this idea of storing energy potential energy. There are lots of different kinds of potential energies or stored energies. Some of them are more hidden than others. For example, you studied chemical potential energy when you were in chemistry. The energy in the bonds was potential energy, a form of this kind of energy. There are lots of different kinds of potential energies out there. There's two things all potential energies have in common. First, all potential energies require the interaction between two or more objects. All potential energies are an interaction between two or more objects. It's in the phrasing. They're going to phrase it this way on the test. You're going to use this word interaction, so you need to be prepared for it. The box has what's called potential energy. In fact, it specifically has what's called gravitational potential energy. In fact, do you remember how much potential energy the box has? You may not know the number, but you know how much work was done on the box. How much work was done by gravity lifting the box there? No, not 300. Negative 300. It's important that we understand that we did 300 joules of work to get the box up here. But 300 joules of work was also done by gravity. It's negative because gravity was trying to bring the box down while we were pushing it up. Remember that? So we define potential energy in terms of how much work was done by the conservative force. We say that an object's potential energy increases if negative work was done by the conservative force. I know it sounds complicated, but the idea here is we had to work to get the box up there. We lose 300 joules of energy. The box gains 300 joules of potential energy by having work done against gravity. So we define increases in potential energy as minus the work done from a conservative force. Luckily, this minutia probably won't be important, but this is a definition. We as humans have defined potential energy this way. We use a capital U for forms of potential energy. And gravitational potential energy, which is the most basic for us, is super easy. It's mg times h minus h naught. Mg was the force of gravity. H was how high we lifted it. It's what we just did, right? We did 15 times 10, that's the mg part, times 2 how high we lifted the box. When we did it with gravity, we had cosine of 180, which made it negative, but we define it as a positive change in potential energy. The box now has something it didn't have before. Now, there are some things about potential energy that are important that you understand. The first is this function. Know this. It's on your equation sheet. Just know it. And I've written it this way on purpose with the h minus h naught, because I want to explain something about it in just a minute. But understand, the box doesn't have this energy. It's an interaction. The box has it because it's near the Earth. This is an interaction between the box and the Earth. This is how they're going to phrase it on the test. The only kind of energy the box can ever have by itself is kinetic. But the box has energy due to its interaction with the Earth. So the box-Earth system have potential energy. This is how they're going to phrase it on your exam. The box-Earth system have potential energy. If there's no Earth, the box would have no potential energy. So again, this is always going to be a system that includes the Earth. Okay, because that didn't go as smoothly as I wanted. So try this one. Take the same box, take the same force. So 15 kilogram box, let's just make it 100 Newton force. And let's make it at 30 degrees. And let's say we pull the box 2 meters along the ground. Let's say there's no friction. Everybody drawing this picture out there? How many forces act on the box? I think there's 3. I think there's going to be gravity acting downwards, right? And I think there's going to be this applied force acting at an angle. And is it touching the ground? So there's a normal force acting upwards. So those are the 3 forces acting on the box. Work could be done by all 3 of them. We should check real quick and see how much work is being done by all of them. The box is being pulled to the right, so can we all kind of agree that this is the direction of motion of the box? Does that make reasonable sense? So this 100 Newton is pulling slightly upwards on the box, but also pulling to the side on the box, correct? So if I wanted to find the work done by gravity, let's say we do that one first. I know the size of the gravitational force. Isn't it 150 newtons? I know the displacement of the box is going to be 2 meters. And then cosine, now I have to choose the angle between the displacement and the weight of the box. What angle is that? If the box is going to go this way and weight is downwards, what is this angle? 90. Does the weight have any component in the direction of motion? No, so 90 degrees. What is the cosine of 90? That unit circle stuff's really screwing you because it's not pi over 2. Cosine of 90 is 0. Check if you need to. But you're supposed to have these. This is why I hate the unit circle. Doesn't stick, but no, the cosine is 0. And the reason the cosine of 90 is 0 in this case is because there is no component of the weight in the direction of motion. So no work is being done by gravity. I'm not sure I had to go through all of this to be able to say that. Is the weight causing the box to go to the right? No. So it doesn't contribute to the work being done in moving the box to the right. If the box were going downward, sure, it would contribute. How about work done by the normal force? Is the normal force doing any work on the box?
No.
Can you look at the picture and just tell?
Yes.
The normal force is up. Is the normal force helping the box go to the right?
No.
No, because it's also going to be cosine of 90 degrees, and that will also be 0. The only time a force does work is if it's in the direction of motion or in the opposite direction of motion. Does the applied force do work on the box?
Yes.
Yeah, it sure does. I don't know why I put, 100 newtons, 2 meters, and cosine of 30 degrees. There we go. This one does work. How much work? This one might require a calculator.
173.2 joules.
172.2 joules.
173.
All right. Isn't this also the net work done on the box? The work done by all the forces?
Yes.
So 173 joules had to equal the change in kinetic energy of the box. Right? Because now this is the work done by an unbalanced force. So you understand that you could set that equal to 1/2 mv squared and tell me how fast the box is going, right? I don't want to spend the time for you to push buttons on your calculator, but you do see that that's something else we could have done. Energy problems are really good at dealing with displacements and velocities. They're very good at it. That's what most of these problems will be about. Although we say the word work and we talk about energy, often the problems that you're going to encounter are going to ask you about how fast the object is going after the work is done, or how far the object slid while work was being done. Those are most often the kinds of questions we have. So when asked on a test, find something's velocity, you may want to use energy to do so. It will usually be the fastest way to solve the problem. Work problems are not good at telling you about time. They are not good about it. Time doesn't show up anywhere in our work discussion, so we don't tend to have problems that we can solve for the time. Also, we tend to not have problems about acceleration. It doesn't show up very much in the work energy functions. So these two things we generally don't see in work. So if you're asked about time or you're asked about acceleration, work and energy is probably not the right thing to use. But if you're asked about velocity and displacement, that's probably a time to use the work energy formula or to use work in general. This. First, there's something called net work. And network is exactly what's implied by the word net. That it is the sum of the work done. So if I look at net work, I mean to add all the work done by individual forces. That's what net work means. But you can do this more than one way. Another way to do this is to calculate the work done by the net force. This is another way to do it. It will achieve the same purpose. Now, however, I'd like you to consider what would happen if the net force wasn't 0, if there was an unbalanced force acting on the object. And what I'm going to do is I want to perform a derivation for you. We've done derivations in the past, and if it's ever been asked of you to reproduce on a test, some of you have a difficult time. This one will not be asked of you to reproduce on a test, but the results have big implications you'll need to memorize the results. But more importantly, you'll need to memorize when you can use the results and when you can't. Does everybody understand what I'm trying to say? All right, good. We're going to start with our definition of work. Work is force times displacement times the cosine of the angle between them. That's our definition of work. So net work would be the net force times the displacement times the cosine of the angle between them. Now, all I've done is replaced force with net force. Now, I want to consider a specific condition, and this will be a little bit challenging for some of you to understand because some of you barely understand what this part is about as it is. But I want to emphasize that in all of this, we're generally talking about individual forces and their direction compared with the displacement. When we talk about this particular example, the net force can do one of two things. It can cause the object to change speed, or it can cause the object to change direction. I want to focus on the situation in which the speed changes and not the direction. Okay. I want to focus on just this type of problem. I know that's narrow, but it's not unusual. Network is done on a car, speeds a car up, or network done on a car slows a car down, right? You apply the accelerator, you apply the brakes. Lots of forces act on the car, but the network speeds it up or slows it down. And that's the kind of situation I want to consider. What this means is I'm only dealing with problems in which the cosine is 0 degrees or the cosine is 180 degrees, where the net force is positive, does positive work, or the net force is negative, does negative work. I want to just consider those situations, okay? And what that does is that allows me to write this as net work equals net force times displacement. We're just going to leave off the cosine part for a few minutes. You'll understand why at the end. Well, I hope you will. All right, so now we're going to do a derivation. Just straight derivation, like a proof. For example, you guys have done proofs in geometry, so you know that you can make substitutions and use postulates and all that kind of stuff. Well, we know that net force equals ma. We're dealing with a Newton's second law problem. So I can replace net force with ma. I can also use the associative property to group together A and delta x. Now, part of the reason I want to do that is I know things about delta x and A. They're related, right? We know that there's relationships like delta x equals 1/2 a t squared plus v naught times t, right? So we have some things about A and delta x already out there. The one I want you to think about is the one that says 2a delta x equals v squared minus v naught squared. This looks familiar, right? So we're dealing with situations in which the acceleration is a constant and focusing us on a particular relationship that works. Now, the reason I'm choosing this one is because of the a delta x in the middle of it. So I want to show that I can do a substitution for a delta x. Everybody see what I've done? So I'm going to substitute this into my function. If you're wondering why, in the laboratory, it's so much easier to find velocity than it is acceleration. So I'm making something that shows us velocity and doesn't have acceleration. Now, I'm going to do a little bit of algebra here. The first bit of algebra I'm going to do is I'm going to distribute the 2. So write this as v squared over 2 minus v naught squared over 2. And the only reason I'm doing that algebra is because I know some of you struggle with algebra. So I'm going to do this in baby steps. And now I can distribute the m, and I'll get 1/2 m v squared minus 1/2 m v naught squared. This has to equal net force times delta x, which has to equal net work. Does this term look familiar to anybody? Some people learned it in middle school, some people didn't. Okay, if you've never seen this term before, that's fine, but it is kind of special in this class. It's known as kinetic energy. And in the universe, we consider this the most basic form of energy. It is the energy of motion. Anything moving has this amount of energy. It's the simplest form of energy to see. What's interesting about it, or what I want you to know about it, is that first v is squared, which means any information about the direction of an object is stripped away. So this can't tell you what direction the object's going, but any motion at all means it has energy. This is what you were measuring when you measured temperature. That's what the whole Kelvin scale was about. Temperature equals the average kinetic energy of the particles of a substance. You may not have been taught that in chemistry, but that's what the PV equals nRT was all about. This is the conversion between energy and temperature. It converts Kelvin to joules. That's what the NR is. Yeah, it's in terms of moles and stuff like that. There is the amount of a substance, because if I have one molecule moving, I'll have more energy if I have two molecules moving, right? So that's why the N is there. But that conversion converts the temperature in Kelvin to joules. Kelvin is a measure of kinetic energy. That's why we always said that there is just absolute zero. There's no negative Kelvin, because what would that mean? The particle's moving negative doesn't matter. Once they stop moving, you're at absolute zero. So it's not that, there's some magical barrier there. It's just that they've stopped moving. What can they do less of if motion is temperature? Now, I want you to understand that we only have, in this class, 3 forms of energy that we'll talk about specifically. This is one of them. You'll need to know all 3 of them. They're all on the equation sheet, but this is the first. So anytime something's moving, it has kinetic energy. And if you don't know, then likely it is moving. You'll understand why I'm saying that tomorrow. But kinetic energy is any motion, and it doesn't have any direction. Units, 1/2 times kilograms times meters per second squared means that the units are kilograms, meter squared per second squared. We talked about units already, but let's just split off the 1 meter, and we get kilograms, meters per second squared times meters, which means Newton meter, which means joule. So the units work out correctly like we would expect. All right? We good? Everybody see where the units are? Good. This is called the work energy theorem. It can only be used in a limited capacity, but anytime work is done by an unbalanced force, it equals the change in kinetic energy. Often it's just written as net work equals delta KE. Okay? Now,